Hello, thank you for watching this talk. So this paper is a sequel to a previous paper, as the title suggests, which was published this year. Okay, so let me introduce this work. So descriptive set theory, as you may know, is a theory that attempts to understand the complexity of subsets of topological spaces, the complexity of describing sets. So it's mainly developed on Polish spaces, which are the completely metrizable spaces, which are the kind of spaces that you find usually in mathematical analysis. Okay, but theoretical computer science needs somewhat other spaces. So when you, for instance, when you study semantics of programming languages or computability theory, you end up with spaces which are far from being Polish. For instance, they are not Hausdorff, they are not Countably-based. So really there is a need to develop descriptive set theory outside Polish spaces. And this was initiated first on domains, okay, which come from semantics of lambda calculus and things like that, and extended to quasi-Polish spaces by Mathieu a few years ago. So this work is a continuation of this program, and we work in topological spaces with admissible representation. So what's a representation? It's a way of encoding the points of the space into symbolic objects. So it's a map, which can be partial, a surjective partial map from the bare space, so the space of infinite sequences of natural numbers. It could also be infinite bit sequences, it's the same. So it maps such symbolic objects to points of the space. So every point has what we call names, which are symbolic representations of the point. And in a represented space, you can do computations. So you can have a Turing machine or an algorithm that takes a point as input by taking any name of the point. So a name is infinite, but it's made of discrete objects, and a program, a Turing machine, can take such a sequence S as oracle. And the main problem we are working on is to understand how to measure the descriptive complexity of sets in such spaces. So let's take a simple example to have some ideas. So we look at the space of real numbers. So this is a Polish space, so descriptive set theory works very well there, but it's also a represented space. So a real number, you can represent it by an infinite sequence of rationals converging to it at some speed. So it's interesting to compare the two approaches from Polish spaces and represented spaces. So how complicated is that set A, the set of inverses of natural numbers? And we have two strategies to answer this question. One is to look at the complexity of testing membership in that set. So how difficult is it to test that a real number is in that set? And the other one is the common one in descriptive set theory, is how to describe the set A in terms of simpler sets, and simpler sets means open sets. So let's answer these two questions. So there is a simple algorithm to test membership in A. So in the real numbers and in continuous spaces, we usually cannot decide sets because of continuity problems, but we can have algorithms that answer in the limit the question. So here we have an algorithm that starts saying no, so it takes a real number as input, it starts saying no, it's not in the set, and then it starts testing essentially whether the point is positive, so it looks for a number n such that it's in this interval, And if it eventually finds it, then it goes to yes. So it's changing its mind from no to yes, and then it starts testing whether x is different from 1 over n. And if eventually the algorithm sees that this is true, so it knows x at sufficient precision to separate it from 1 over n, then it changes mind to no. So the algorithm tests A with at most 2 mind changes. Okay. And the other way is how to describe A in terms of open sets. So this is easy. It's a difference of 2 open sets, the positive number minus the numbers that are not inverses of natural numbers. So we have these 2 things which are actually equivalent. So for subsets of real numbers, it's always equivalent to be decidable with 2 mind changes, so starting with no, and to be a difference of 2 effective open sets, which are open sets which can be described by an algorithm. So the algorithmic and topological viewpoints are equivalent on the real numbers. Now let's just rephrase the algorithm formulation, because algorithms don't take real numbers, they take names, encodings of real numbers as input. So what's the algorithmic complexity of the set? It's actually measuring the complexity of the set of names of points in the set. So the algorithmic complexity of the set is actually the complexity of the preimage of the set under the representation. And this equivalence can be rephrased by saying the preimage of A is a difference of 2 effective open sets if and only if A is a difference of 2 effective open sets. So in general, we have these 2 notions of complexity for a set: the topological complexity of A and the topological complexity of its preimage. And the question is, how do they relate in general? Do they coincide, and if not, then when do they coincide? So that's the goal of this work. So first, to be clear about what we mean by topological complexity, we use the usual hierarchies in descriptive set theory, which classifies sets according to their descriptions in terms of open sets. So in the Borel hierarchy, you have the open set, sigma 1, the closed set, pi 1. Sigma 2 is the countable unions of differences of open sets, and so on. You have all this hierarchy. And when you look in the first levels, so below delta 2, you can refine the Borel hierarchy and have this whole Hausdorff difference hierarchy, where you just count the number of finite Boolean operations. So for instance, you start with the open set, the closed sets, and D2 is the differences of 2 open sets. D3 is the differences of 3 open sets, and you can go on forever, well, not forever, but until the first uncountable ordinal, and you cover the delta 2 sets like that. Okay, so this is how we measure topological complexity. So now as suggested by the first slides, we define the symbolic complexity of a set. So we could also say the algorithmic complexity, but we choose to call it symbolic complexity of a set. So it's the complexity of the symbolic representation of the set. So the complexity of the set of names of points in the set. So it has a set has symbolic complexity sigma 2 if the preimage is in sigma 2. And we write that the class, the corresponding class, gamma with square brackets. So the first observations are that, so we're working in topological spaces with a representation which is admissible in some sense, which means it respects the topology. And the consequences of this are that at the very first level, the sigma 1 level, we have always agreement. So a set is open if and only if its preimage is open. Another consequence of being admissible is that the representation is continuous. So if a set has complexity gamma, then its preimage under delta has also complexity gamma. So we always have this inclusion. Okay, but in general we will see that we may not have equality. So the main problem is for which spaces and which complexity classes, complexity levels gamma, do we have equality. So let's first see a space where we do not have equality. So we will see next a space where they are different, symbolic and topological complexity are different, and then we will see a large class of spaces where we have agreement. And then we will eventually come to the results of this paper after these 2 points. So first, a space with disagreement. So it's the space of polynomials with real coefficients. So here, a polynomial is represented in the following way. You first give an upper bound on the degree, some n like that, and you give a description of the coefficients. They are real numbers, so you know how to represent them, and that's the representation of your polynomial. It's important to have an upper bound on the degree and not the exact degree for some reasons. And in that space, that's the picture that we get. So we have agreement from level delta 2, so everything above symbolic and topological complexity agree. However, below delta 2 there is this strange gap so there is a set here which has symbolic complexity d2, which means essentially there is an algorithm with 2 mind changes to test the set, which is delta 2 in terms of topology, but it's not below. Okay, so we have inclusion of this class into delta 2, but we also have a set there which is not below delta 2. So it's really there is this very big gap. Okay, so we have disagreement at the first levels and then agreement after. I just put quickly examples of sets witnessing the difference. I won't insist on them, but you can pause and try to see a set which has symbolic complexity d2 but not topological complexity d2, and the worst one is this more complicated set which has symbolic complexity d2 but topologically it's not below delta 2. It is delta 2 but not below. Good, so now let's look at a large class of spaces for which we always have agreement between symbolic and topological complexity, and these are the countably-based spaces. So it was proved by Mathieu that for countably-based spaces we have agreement at every complexity level, every Borel complexity level. And we proved recently that they are essentially the only spaces where everything works very well, in the sense that they are the only spaces where at the first level above sigma 1, so which is differences of 2 open sets, at the first level we have agreement in a uniform way, which means we can translate between the 2 descriptions in a uniform continuous way. So they are the only spaces where this happens. So that there can be spaces which are not countably based, where we have equality here, but in a non-uniform way. So on countably based spaces we have this nice picture where everything agrees from the left side and the right side. So now let's come to the results of the paper. So first we investigate hardness on represented spaces. So what's hardness? As you may know, so it's a way to give lower bounds on complexity of sets. So how do you prove that a set is not sigma 2? Well, the usual way is to prove that it's pi2 hard. Okay, so every pi2 set is continuously reducible to A. And essentially that's the only way, because there is this nice wage lemma from classical descriptive set theory in Polish spaces, which tells you a set is not in some level if and only if it's hard for the complement class. So this is true under some assumption of the class, but this is a very nice equivalence. So what happens in represented spaces? Well, it turns out that this hardness criterion can be still works, but we have to replace topological complexity with symbolic complexity. So hardness is actually related not to topological complexity, but to symbolic complexity, which may seem surprising because hardness is a topological notion using continuous reduction, and symbolic complexity is about representations. But we have this. So how to capture topological complexity? How to prove that A is not in gamma, in the topological class gamma? So we adapt the notion of hardness and propose this weaker version of hardness, we call hard star. So a set is hard star if when we take any weaker topology on the space, which is countably-based, A becomes hard for gamma in that topology. And so it's a bit cumbersome, but it turns out that it works very well, and hard star exactly captures topological complexity. So we recover the hardness criterion for topological complexity with hard star notion. And for completeness, let's just put the previous result, where we see clearly that hardness is related to symbolic complexity and hardness star is related to topological complexity. And now we will look at a large class of spaces where very interesting and complicated things happen, and we try to classify as much as possible the relation between symbolic and topological complexity. So they are the spaces of open sets. Okay, so represented spaces and admissibly represented spaces, they are some class of topological spaces which behave very well in terms of categories. So it's a Cartesian closed category, so you have function spaces, and in particular, if you take some space there, some admissibly represented space, then the space of open sets is also in this category. So you have a very natural representation of the space of open sets, and the topology associated is the Scott topology, which is a very standard topology. Okay, so we have this space with the Scott topology, a natural representation, and we want to investigate descriptive complexity on that space and compare the symbolic and the topological versions of complexity. So the first result is that at the first levels of the difference hierarchy, we always have agreement between symbolic and topological complexity. So you may remember that for the space of polynomials, we had disagreement at the very first level. But for spaces of open sets, it's not the case. So for all the finite levels of the difference hierarchy, we have equality. And we will see that at that level, at the first infinite level, omega, we sometimes have disagreement. But we, of course, always have this inclusion. So now let's see at higher complexity levels. And to do this investigation, we will restrict our attention to the case when X is a Polish space. So it's more convenient, and we manage to have a quite complete picture in that case. And it turns out that the answer depends on the compactness properties of X. The best case is the case when X is locally compact, for instance the real numbers, and the worst case is when X is not sigma compact, for instance the Baire space. So we introduce a classification of Polish spaces into 2 and into 4 disjoint classes. They cover all the Polish spaces. So we start from the locally compact ones, class 1, and we end up with the non-sigma compact spaces, class 4. And in between, we look at the number of points where local compactness is violated. So we look at this subset of points with no compact neighborhood, and depending on whether it's finite or infinite, we have these two intermediate classes. So class 1, an example is R, and class 4, an example is the bare space. So for class 1, everything is fine because O of X is countably based, so we have full agreement between symbolic and topological complexity there. And for the other classes, so we get a quite complete picture where you see all the relations that we have between the levels. Okay, so we see, for instance, in class 2 that we have something similar to the polynomials. So we have some disagreement in the beginning. For polynomials it was below delta 2, here it's delta 3. But after delta 3, symbolic and topological complexity always agree. So there is only a problem in the beginning, but after everything is fine. In class 3, we have disagreement at all levels starting from sigma 2. So we don't know exactly what happens below. This remains to be studied. And the very worst case is class 4, for instance the bare space. So we are looking at the space of open subsets of the bare space here, and there is a set which has symbolic complexity sigma 2, but which is not Borel, so it goes above the Borel hierarchy. So it's there is a huge gap there. So yeah, here maybe the most important things to look at are these red arrows, which can be phrased this way. So here there is a set with symbolic complexity d omega, which is delta 3 complete star. Okay, so it's delta 3 and not below in terms of topology. And we see that we need to use this notion of hard star to capture the topological complexity. And all of them can be phrased this way, and there we have a set with symbolic complexity sigma 2, which is not Borel. Okay, so we are coming to the end of the talk, but so we have all these results which are nice, but they don't really explain what happens and why symbolic and topological complexity differ. So the point is that from the ingredients that we use in the proof, we come to some conclusion and some kind of explanation of this phenomenon, which is as follows. So you may know that most topological notions can be expressed in at least two ways, so in terms of open sets or in terms of converging sequences. For instance, a function is continuous if the preimage of open sets are open. A function is sequentially continuous if it sends converging sequences to converging sequences. And you have similar notions for compactness, closure, and so on. And you have the topological and the sequential notions. It turns out that they all coincide for countably-based spaces, but they might differ on other spaces. And we think that this is the explanation. So this difference explains the difference between topological and symbolic complexity. And we suggest that we could extend this array, this table, to add this line, and saying that symbolic complexity can be thought as the sequential counterpart of topological complexity, which means that algorithms are more sensitive to the sequential aspects of a space than to the topological ones. So the complexity of an algorithm testing a set is more related to the sequential aspects of the space rather than to the topological ones. But this suggestion remains to be investigated further to give more evidence about this intuition. So this is the end, and thank you again for watching. I hope you will join for the discussion session of the conference.